Good day, ladies and gents. Welcome to this next part of our worked example where we're working out the loading to be applied to an industrial structure to SANS 10160 part 1, 2 and 3. So this is the South African loading code. Now you should have watched the first part of the video which calculated all the wind loading with external, internal pressure coefficients, pressures, etc. We're now going to get on to the next part of the question, looking at the permanent loads and the imposed loads that must be applied to the structure along with load combinations. So here you'll see the questions, just to reiterate what we've been through previously. Determine the imposed and permanent loads to be applied to the structure's point loads from the purlins. Rafter and column loads will be added by the software used. List the load combinations for the structure. Assume that there is only two wind load cases, W1 and W2, where in fact there could be 4 wind directions, 2 CPI factors, 4 wind roof CP orientations, etc. So 32 wind cases. We're only going to consider 2 to keep it simple. Now, as I mentioned previously, an experienced engineer could reduce that number of wind cases quite significantly. But here's a cross-section through our structure. So it is a typical portal framed building, and we want to now analyze the structure and break it down into a model we can feed into a finite element program. Now we need to apply loads at different positions, so we've got to break it down into a bunch of nodes. So I've drawn blue lines then where we're going to model the beams as beam elements, and now we have to decide how many nodes we want. I mean, if we really wanted a coarse analysis, we could actually just have nodes there and that would be fine. But with all the purlins, it makes sense that we add some extra nodes where the purlins are, or on top, to analyze it. And then we could also add where the girts are on the side to apply loads there. But for now, to keep the model simple, I'm only going to add purlins on top. If you wanted to, you could have 3 very closely spaced nodes at the top to account for the apex and then the purlin each side. So that would be in this vicinity, but I'm going to just have a single node at the top. And remember, your model should match the accuracy of the loads you have and also what you are designing. And remember, in steel design, the loads are somewhat uncertain, especially wind loads, and also the beam sizes we're working with are often 20% different from one to another. So either you're with a 305, 102.25, or the next size up or the next size down, and so that would be a 20% difference easily in size. So a 0.5 or 1% different in your answer is not really going to make a huge difference, but you should be accurate as possible, but also realizing that this is not perfect. So here's the model I've done. So I've added nodes to the structure, and now I'm just going to add numbers to the structure, number to the nodes, so it's easy to discuss, and then we're going to start getting into some of the calcs. So here you can see I've added nodes to the structure and then also numbered the nodes, so we've got something to deal with. We're first going to work out the permanent loads and then the imposed loads, and then also just look at how we're going to apply to the different nodes throughout the structure. So I'm going to go ahead and write out the details and then we'll discuss through them. So here we are coming back to our structure, and I've just added firstly some dimensions to it. With simplifying it into the nodes along the top, I've just uniformly distributed those nodes at 1.875 meters. But once again, you could do it a little bit more accurately, especially around node 6, but this will make the calcs a lot easier now for the analysis. Now, when it comes to loads on nodes 3 to 9, so that's all our middle nodes, so they've got tributary area from both sides. So when we're looking at, for instance, node 3, I would want to take all the load in that zone and apply it to node 3. So that means the purlins to be applied, the rafter, but once again we're told that the rafter is considered by the software, so we're going to not consider it here. And then also we need to consider the sheeting, and other items, but one thing to remember is that our sheeting is inclined at an angle. Our sheeting sits on top here. It's at a 10-degree slope, so in the 1.875 horizontal distance, there is 1.875 divided by cos 10 of sheeting. But the imposed loads we're going to look at below, those are just set more or less according to floor area. So it's per horizontal distance. So we're not going to take we'll divide by the cos of 1.875 for a load per floor area, but we will increase the length when it is a diagonal area. So here you can see now, coming back to the calcs, we've got our permanent loads, our purlins. We've got the self-weight of the purlins, 5.1 kilograms per meter from the red book, and then we multiply it out. And this is then a 5-meter span between bays, so there's 2.5 meters each side of the truss or the raft or the portal frame, and then the sheeting, 6 kilograms per square meter, but as I mentioned, that's on a diagonal, so we divide by cos 10, and then the insulation, that's 3 kilograms per square meter, so once again divide by cos 10. We add all of those up and we get 1 kilonewton per node to be applied as permanent loads, so that's about 100 kilograms. So it's one large man, well, one rugby player per node we will be applying. Then we go into our imposed loads. Firstly here, services. Just be careful and see what I've done here. Now, I've taken services as an imposed load, but here it says, this is straight from the code, self-weight of constructed works. And then part C, include the structural and non-structural element, including fixed services as well as weight of earth and ballast. But I have taken it as an imposed load, not a permanent load. So why is that? Well, firstly, this is fixed services, and in a industrial warehouse, so things change. You have processes, and then they bring in a new process or a new machine, and suddenly people are hanging pipes from the roof or ducts or whatever it is. So suddenly you've got 20 new pipes or a big diameter water pipe hanging from one side of the roof. So it's very variable. It could be pattern loaded. It could change significantly with time and such items like that. So I'm rather going to err on the conservative side and assume it is a live load, so it has a higher factor, but also it can be a factor of 0. So it might not be there, and that's true in such an industrial warehouse. Maybe the process changes and now you don't have any services hanging from the roof, and that can actually resist uplift wind load. So both it not being there or it being there and being more could be worst load case, depending on what you are looking at. So hence I've taken it specifically for this case as an imposed load. However, in a formal building where the services are pipes and sprinklers and the likes that are relatively constant, unlikely to change much in the life of building, you should be taking them as permanent loads. But this does highlight how you often need to apply engineering judgment and say what would happen in the future and what is the most conservative but realistic load, and then go with that. You may not need to just blindly follow the code. So coming back, where we have our calculations, our imposed loads, services, and then I've noted how I have broken the rules with the services and treated it as an imposed load, but this is going to give me higher loads because I've actually going to have to use a 1.6 factor for it. Then an inaccessible roof, it's what we are designing, the portal frame, is greater than 15 square meters. If we were designing one purlin or a small area, we might need to adjust this load, but we're designing the whole portal frame. It's an inaccessible roof from class H1, H2, so I'm just going to show you that table up here. From the table 5, and here's an inaccessible roof, and then we're going to then use it either for normal operations or during maintenance and repair, and then we end up with 0.25 kPa. We could also have a point load of 1 kilonewton over a small area, but since what we're designing is much greater than the small area, so you can see this is for over 0.1 by 0.1, but if you take 0.25 kPa multiplied by the area we're dealing with, you end up with a much higher total load than if you consider the point load on its own. You apply either one or the other, not both together. And since what we're doing is covering a large area, the distributed load will govern and not the point load. So we're only going to consider the distributed load in this case, but it wouldn't be wrong to take the point load as well. And just as a note, once again, just about engineering judgment, here it says accessible flat roofs, a load of 2. Now, for one of our old clients, we would never use a value of 2. We used a value of 5 or more because, for instance, when they had a flat roof in a warehouse or in one of their factories, you would have staff that would run out of space in the factory and suddenly they would put heavy switchgear or electrical equipment on the roof, and I am aware of one case where they put heavy equipment and it fell through the roof. So 2 kPa wasn't sufficient for the use in that factory, so it was not a good idea. So for those specific requirements, we increased it to 5 in general because of safety implications and knowing that 20 years from now someone might put something heavy on that concrete roof when they have a new electrical piece of equipment or so. So keep these things in the back of your mind. We have good code guidelines, but sometimes code guidelines cannot account for what your client will do in real life, and you should try see what might be a realistic scenario that could occur. So here's now our inaccessible roof, 0.25 kPa times by the spans and areas, and we get to a total point load of 5.56. So if you think about that, that's a fair amount. That's 5 to 6 rugby players standing on each point load at a time. These are now the internal point loads we've done. So for loads 3 to 9, we now need to do the external point loads, so loads 2 and 10. And if you have a look at those will now have a different tributary area. And so we're going to have half the amount of sheeting, half the amount of imposed load. If we had a big cantilever on the side, maybe not, but it's roughly half the amount of imposed load. And then also now we have column load, but once again I said column is included in the software, but we do have side sheeting all along here. Actually, let me put this in red to be consistent. So I've got side sheeting, and I had some girts on the side. So I need to add those in. And just to highlight how our loads might differ depending on our discretization of the model, I've got one node at the top and one node at the bottom. So I'm going to take all the load in this zone and basically divided it by 2. So all the wall load will be divided by 2. But if I added nodes along here, I could then divide it by more and more. So then I might take the loads and divide it by 3, 4, or 5, and then apply it as more point loads up the height. It depends on the accuracy you need. It probably won't make a huge difference in your final result, but this is why I'm only dividing by 2, but you could divide it by more depending on what your how fine your mesh is for your beam elements, and also just how much effort you're going to and what level of accuracy you need on the model. If you're just working out a foundation load, it makes very little difference, and so you just need to see what you're trying to analyze. But once again, I'm now going to take the load from the roof, divide by 2, and then the load from the side sheeting, the girts on the side, and then also go half of the column up, half of the column down. So I'm going to write all those out and then discuss them. So here we've got everything written out, what we've just explained. We've got half purlin plus column cladding being applied at 2 and 10. We've got our purlins, we've got our sheeting. So this is then the side wall and the side wall and roof cladding. And just a note, because often this gets asked, purlins girts, why do I have 2.5 number that I'm including here? Coming back to this, I have one on the roof, one at the top of the column, and then this one here, half of the load I'm assuming going up, half of the load going down. So 1, 1, 0.5. So that's why there's 2.5 purlins or girts I've applied to the structure here. One from roof, one from side, and then half from halfway up. And that'll depend on the physical number of purlins and girts on your structure. And then coming back to the calculations. So yeah, then we've got our insulation, imposed load using half of the roof load previously, and there we have our dead load and imposed load calculated. Final thing, at node 6, add extra purlin load, because you'll see at the apex there was an extra purlin there. So in our model we would have added the loads from nodes from 3 to 9, and then we'd added just an extra 0.25 or whatever the purlin weight was at node 6. Okay, so that takes us through then all the permanent and imposed loads on the structure, looking then at how do we calculate them for a sort of typical portal frame structure like this, and then also how do we account for the insulation, the cladding, and all the various things on these sides. We're going to focus on question 6 now, where we have to generate the load combinations for the structure. We're going to generate every possible load combination, so it's going to end up being a very large number of equations we produce. However, in reality, you wouldn't need all of them, you would only need some of them, and you'd be able to identify which are likely to govern. But for completeness and to understand the approach, we're going to produce all of them. Now, here you'll see the STRP load combinations equation and SDR load combinations equation. Firstly, what we have is then the permanent loads, and then a pre-stressing action, and then the leading variable action. We don't have any pre-stressing in this case, so that's why I've crossed out P. And then for STRP, remember that's permanent was almost governing or leading. So this isn't the case. We've got heavy permanent loads. This load combination typically governs. In our building, it is unlikely to govern. Our wind loading and our imposed is far greater than our dead loading or permanent, so this is unlikely to govern, but we're putting in for completeness. But here, just remember, we only have one variable action. So we only have one leading variable action plus the permanent load at maximum, and then we're going to get on to SDR, which is likely to govern. There we have our permanent action, and then we have our leading variable plus accompanying variables. So for instance, this would be the general maintenance loading plus then the crawl beam at the apex. So two loads that are separate, that act separately, that are not correlated, and we adjust the second one to account for the fact that the chance of it being at its maximum at the same time as the other one's quite low. So when it comes to this, we need to try all different types of imposed loads as leading. So this term could be wind, it could be the maintenance load, it could be the roof crawl beam, it could be any of them. We don't know. So we're going to generate a bunch of different combinations and test them and see which gives us the worst bending moment or axial load or reaction, and use the worst case one to design. And we might even find that the worst axial load in the column is from one combination, the worst beam design is from another combination, and the worst foundations from another combination. We're going to test all of them, and then depending on what we're designing, we'll pick the worst, but any could govern. And then we will just keep rotating through. So we're going to try all the wind as leading, all the maintenance roof load as leading, and services, and then all the roof, etc., etc., so roof crawl. So we're going to try all these different loads and see what happens. And then when one load is leading, that which is not correlated, that which is not linked to it, for instance, maintenance and a crawl beam at the middle of the roof, they act independently. They are caused by two different entities. So the chance of the maximum crawl beam load at the apex happening at the same time as the maintenance load is quite low, so we keep them separately and we reduce the accompanying action. And then once again, all of these actions will also be accompanying actions, but reduced to account for the fact that when they're combined with the other one, they're not going to be at their maximum value. So that's going to be our approach now. I'm going to write out the different factors we're going to be using, and then we will discuss through them. So here we have the different load cases. First, you've got GK permanent, and just remember, GK I'm just referring to as total permanent load now, and then we've got QK1 imposed, and then QK2, which is our 6 kilonewton point load at the apex, which is from a hoist. So there's some sort of crawl beam or hoist that they fix to the top of the middle of the structure and then hoist stuff up and down. Very common in industrial structures for lifting equipment or machines in and out. We've got W1, which is wind load, and for example, theta is 0 degrees, and it will be coupled with some CPI factor. So it'll be the total wind load, CPE and CPI. Let me just make that clear. Otherwise, we'd have to have a separate load case of, for instance, CPI, and then add that case in with W1 or W2 or independently each time. Now, our combination factors, these come from SANS 10160 Part 1. So this is how much, for instance, imposed load is there when the hoist is at its maximum load. So these allow for the fact that the statistical chance of both being at maximum is not that likely. So we've got about 60% of the load we used for accompanying our actions for general imposed loads, assuming heavy industrial, 0 for wind, and then 0.3 for SLS wind. Now, the 0 factor for wind simply comes from the fact that when the worst wind load in 50 years acts, it's a very short event of a couple of seconds, and then the chance of the maximum imposed load happening at the time, or even very much imposed load happening at the time, is quite low, so it is set at 1. There are disputes regarding that factor, but that is according to the code. And then for serviceability limit state, it's set at 0.3. Now, favorable and unfavorable loads, so these are partial factors to be applied directly to our loads. So if for permanent loads, imposed loads, and then wind, for the STRP case and then the SDR, we've either got an unfavorable or a favorable action. And then you'll see it's 0 for the imposed load, so it might not be there. And then SLS loads. So we just take a little bit extra for permanent loads because maybe the concrete floor is a little bit thicker than we thought, or they've added some tiles or something like that. So we've got a little bit of a partial factor, but in general, the values are often around 1 for the rest of these. So that's day-to-day operation, SLS, where the other two, remember, are ULS values for STR and STRP. I'm going to set up quite a big table now and then put in all the values. As I said, this is quite a laborious task to put all this together, but hopefully it illustrates how you would go determining all the load combinations for a structure. So here I've set up a table to create all the different load combinations. Normally it would be a lot easier just to write it out. For instance, load combination 1 equals 1.2 GK plus 1.6 QK. In most situations it's a lot easier to write it out like that. The only reason I've put it into a table is so you can just see how the factors are allocated and how we have a sort of a comprehensive list of all the load combinations. Firstly, we've got our STR cases. We've got all the way down, and then I'm going to fill in those details. And then once again, remember STR, the partial factor is 1.35 for the permanent, so it's kind of a dead load, or permanent load is a leading variable. And then we apply all the other loads with it, but with factors of 1. And we don't apply these together because they are not correlated values, i.e. wind load 1 cannot happen at the same time as wind load 2, and the imposed loads act at different times. So let me just add the subscripts, QK1. So these are the loads we are now applying. So there's all our STR cases, 5 of them because we have the just the permanent load on its own, and then the 4 different imposed loads. By inspection, you'll see load combination 1 is pretty much a waste of time. We wouldn't need to do it. And then by inspection, we'd probably be able to tell which of the other ones would govern and only need 1 or 2 of them. But once again, as soon as we get to the STR cases, all of the STRP are unlikely to be needed. We're going to continue now with STR cases. And here what we're going to do is once again create all the cases. So I'm going to write it all out and then explain it to you. So here I've generated all the different load combinations, and firstly what's been done is 1.2 has been set for all the permanent loads. So this is when the permanent load makes the loss worse, it makes it higher. This is an unfavorable load combination, and then we'll run through again where we would have all these load combinations again, but with 0.9 instead of 1.2. First, what I've taken is the imposed load, the general roof load, and put all of those as 1.6. And then what happens is, initially, it's just it on its own, then it's it on its own, plus then, for instance, the apex crawl beam. Then we have it plus either the wind cases. I haven't made the wind cases different because they multiply by 0, so these actually cases totally disappear, so it's the same as load combination 7 anyway, so we don't need LC9, but I'm just showing you where this comes from. Then we're going on to load combination 10. Now I've made the apex load governing and then put it either with the roof load or with the wind, but once again the wind disappears because of the fact that there is a 0 combination factor. Then we move on, and now the wind load is leading. And then we combine it either with the apex load, either with the roof load or the apex load, or both. And just remember, you'll see here, coming back to my equation, it is a sum of I is greater than 1. So these are all the accompanying actions, so they can be multiple accompanying actions included. So that's what we've got here. We have multiple accompanying actions we've added on, but all reduced accordingly. So that's why that and that have been reduced accordingly. Then we do the exact same thing now with the wind case 2, and run through that and then combine it with everything else. Once again, we do not combine the wind loads together because they do not act at the same time. Either it's load from the one way or it's load from the other way. It's not loads. They can't act together. If you do have, for instance, a 45-degree wind load case for an unusual structure, you would treat that as a separate wind load W3, and you treat that. But once again, we've only got 2 load cases for wind, and you could have a lot more than that, so just remember that. But now we would have to go through and repeat this process again for the STR cases, but with 0.9 QK. So all of this would be repeated right from here to here. We would need to repeat with 0.9. That ends up 35 wind load combinations, and now we've already reduced the amount of wind cases. And you'll see, that's just unfeasible. For a simple portal frame to have 35 combinations is just crazy. You're going to end up killing yourself in terms of the analysis trying to make sure you've got the right case. So what you would then do now is to go through and pick out which of these do you actually need. And you would normally be able to do this before you even write all of them out to try see which of these are likely to govern. And you could identify this fairly quickly. And we're just going to highlight a couple that may govern. As I said, for our specific case, the permanent load is much lighter than the imposed load. So STR is much more likely to govern. So looking at this thing now, just see of the STR cases, which ones are likely to govern. We'll load combination 8, because that is the maximum amount of downward load. If the we'd need to then see which of the imposed loads would govern, but load combination 8 or 11, very likely to govern. Those are 2 we'd probably very quickly go have a look at in terms of worst case. Then potentially load combination 13, but if this is a suction load, then but if this is a suction load, we would want 0.9 uplift, but with 0.9 QK. This is a very possible one if uplift. Same thing for load case, where is it now? Load case 17. That would very possibly govern, if it's uplift, then the 0.9 QK uplift plus minimum downward load likely to govern. And let's see now, if it was different, for instance, if these were downward wind pressures, then we would probably be looking at load combination 16 and load combinations 20. If W downwards. If it's a net downward pressure, those are the load combinations likely to govern. And really see, from 35 cases, we've reduced to a lot less than that, about 6 or 7, and very likely that those ones would be then what you would need to work with, but would require some judgment. So that takes us through then generating a set of load combinations for the structure, and then how to identify the potential worst case ones. And just to highlight what I mentioned earlier, we took one imposed load at a time. So either it was the first imposed loading, or it was the second load imposed load leading, or it was the wind load leading, or it was the other wind load leading, and then we combined it with everything else. We didn't know which one was going to govern offhand, so we went and created a whole bunch. Now what we're going to do is go through and create the serviceability limit state load combinations, and then discuss through those. I've just noticed one thing you quickly need to correct. The case with the favorable imposed load, that should be 0.9 G, not 0.9 Q. So just quickly update your calculations. That is the correct value here. We are adjusting that column. Now we're going to go on to the SLS loads. And here, once again, we've set up a table. We've set up load combinations. I'm going to write it all out, and then we'll discuss through it. So here you can see I've set up the serviceability limit state load combinations, and just to make things clear, I've added an S to it, just to realize that this is it's more or less the same combinations above, but you will see there are just some discrepancies, because now we have wind loads which have, for instance, a psi factor of not 0. So here we've gone ahead, when we first just applied the 1.1 factor to all of the load combinations. So this is the unfavorable permanent load, and then we've gone and first applied the imposed load 1 all the way down, combined it with the apex load, combined it with the wind, combined it imposed and wind, etc. So you can see there's some extra cases as per above, simply because we have a non-zero combination factor for the wind. We do the exact same thing then for the apex load leading, combine it with all the other different ones to find out which is the worst case. And here you'll see for all of the wind, once again, I do not have W1 and W2 acting at the same time, and then I have the wind load leading, no combination factor, so no combination factor front, that disappears, it's just the pure partial factor. Combine it with imposed 2, both of them, same thing for W2. Go through and get 21 serviceability combinations, and then you'll see we have to do this all again, but instead with 1 times the dead load. So that would be then for when the dead load makes the load less. Now, once again, we can identify quite quickly cases that are likely to govern. First, we would be looking for the maximum downward load, and that would then likely to be, for instance, this. If wind is a suction pressure, then that one is likely to govern, or that one. If wind is opposing your imposed load, then those two are likely to govern. Once again, for maximum suction, you could have maximum suction would be that, but then once again you'd have with minimum dead load, so the one value, or you would have that one, that would be likely to govern. If the wind is acting downwards, if you have a load case where the wind is downward, then there are a couple of other ones that could govern. Let's have a look which ones may be. There are various different options. So that would be, for instance, for wind downwards, that would be likely to govern. Or oops, sorry, I've just highlighted the wrong one, my apologies. I meant to highlight ones further down. This one or this one are likely to govern when there's a downward case. There could be others that could govern different parts of the structure, so I'm not saying these are everything, but it gives you a good sort of a quick overview of which combinations you would look at to get to the worst case load somewhere in your structure. And then just final comment, finishing this one off, remember all of these were uncorrelated values, but you can have a time when loads are correlated. For instance, you've got a machine and you've got a lateral load and a vertical load, and the machine causes the same two at the same time. And then in that case, you could have them, for instance, you'd have your 1.2 GK. If you were considering them separately, if they are correlated that means they can act at the same time, then you could actually put them together. But when they are caused by separate things and they cannot be a maximum at the same time, we split them. But once again, when they're correlated, then you could have them both at their maximum at the same time. But you'd have to have a look at physically what is causing it, and is that possible. Okay, so that's given an overview of generating the load combinations and going through and how we get together the different combinations for a structure, and then also how we would simplify them to get to the worst case. Thank you.